Hello guys, welcome back to this second video of this Peridynamics YouTube video tutorial. In this part, first of all, I would like to start by speaking what we saw last time, and it was basically a very brief introduction into what is peridynamics and what has been the main motivation behind using this currently new technology in the computational mechanics community. The idea is, as I explained before, it's a reformulation of classical continuum mechanics, where instead of working with stresses and strains, you are working only with forces and displacements. And this is very important because you are not assuming any continuity on the displacement field as you have to when using partial differential equations. So this has one of the main advantages, and this is the simulation of fracture and propagation. And in our last time, we also spoke about a little bit about how damage can be introduced by breaking bonds in the peridynamic formulation. And what are those bonds? And perhaps this is something that I would like to go a little bit deeper into today, like just how, like in a better way to better explain what is this bond new notation, this state-based new notation in general. And I will also speak about how can you relate the peridynamic equation of motion with an actual Peridynamics code that will do the work about simulating the materials and the solids that you are interested in. So without any further delay, let's jump into it. So last time we spoke about a new notation that has been introduced, but I did not specify what is exactly these capital letters and scalar small letters. So in the previous section, we talked that how damage may be introduced as a bond stretch. And when we are talking about a bond stretch, we are talking about how much the bond is stretching from respect to the original configuration. And this is denoted as a scalar. One important thing, lowercase letters and underlined are referred to states. States means those variables that are underlined as in here. And why they call them states? Because they are referring to bonds in particular. And if they are lowercase, that means a scalar value. Scalar value means number one, either 2 or 3 or 4, just one number, whereas capital letters indicate a vector acting upon a specific bond. And this vector has, as you may know, 3 components. Has a component in the x direction, in the y direction, and in the z direction. So as in here, we are in order to compute the stretch of this bond, you need the vector position y. Current vector position y has 3 components, but it's obtaining the absolute, or this means the magnitude of this. That means the first component times the second component times the third component. Each of these terms, it's being squared, and then it's obtain a squared root of all these 3 components to get this absolute value. Less than the original position of this bond, which is the x, y, and z again, divided by the original position. This will give you a stretch, which will be a scalar. That's why it is represented as in lowercase letters with the parameter s here, whereas these ones were vectors that then are converted into scalars when obtaining its magnitude, right? So in other terms, the numerator on this expression, it's a scalar quantity divided by another scalar quantity. It will give you the scalar again, right? And whereas here, another thing that I did not mention was like, then if this stretch is bigger than a certain value, then it breaks, the bond breaks, and then the force is no longer considered because the parameter d will be equal to 1. So 1 minus 1, it will become 0, and there is nothing else. But here, in order to get the force state is a vector quantity. So it means it has 3 components. So you need to compute the material force state, which can be expressed as a scalar with the lowercase letter t, which will be acting in one particular bond, multiplied by the m, and the m is a unit vector. M, it's the deformation of the deformation where the force is acting upon. Yeah. So anyway, this is just a brief explanation about why we use lowercase for denoting scalars and capital letters for denoting vectors. But notice that here we are not talking about any stress tensor or higher order tensorial quantities, because we are only working in the peridynamics formulation with either scalars or vectors, and that's it. No tensors here so far. You can compute tensors, but that's another issue which is not actually covered in this part. But all you need are actually scalars and vectors. So I was talking about, this is the peridynamic equation of motion. Recapitulating, the F is a force function, and originally we were looking at this expression expressed as capital letters T, which are acting forces upon a specific bond, and the bond is being formed by the particles Q and X, and this in between brackets we are putting X because this is acting on the neighborhood of this parameter X here. Yeah, whereas in this case the force is acting on the particle Q, and the bond is being computed as X minus Q instead of previously Q minus X. Why is this important? Well, the important thing here is sometimes I find it difficult to understand this expression. What exactly does this mean, and how is it coded? And one easy way to looking at it is actually going into a peridynamics code that has been already developed and seeing here what is the explanation. I would suggest for these cases to use, you can go GitHub, Peridigm, and inside this code, if you go into the source files folder and then into the materials folder, you can go all the way down into, there are several material models that are implemented into this Peridigm code, but you can go all the way down into the, let's see, the elastic CXX file. So in this part, how you will see the function compute internal force linear elastics, and here it will be useful to understand how are these bonds computed and so on. So previously we were looking that in order to compute the force, yeah, you need an horizon, and this horizon is formed by bonds that are inside this domain, and these bonds belong all to the particle X, whereas all the bonds are formed from the particle Q and other Q's that are inside this circle, right? So if we look at this code here, we can see immediately that we have here two for loops. One is for the particle P and another is for the particle Q. Well, in this case it's called N, but let's imagine that this is Q, okay? So in this first loop, we will be looping over all the particles X in all my domain, right? But in this second loop here, we will be looping only for all the particles Q that are inside the domain of, or inside the horizon of the particle P, which in this case, it will be looping over all particles Q inside the domain of X, inside the horizon of X, yeah? So this is one first thing. Then here we can see how it is being computed the components of the vector of the original position X here by subtracting xp minus x. It will give you the first component, the second component, that means the y component, and then the z component of the original position vector X, which is this one here, X. Yes, it's not computing yet the magnitude, it's just computing the vector itself of this bond. This is how a bond is being formed. And then the y, how it is being computed as y the same way, the first and the second and the third component. Yeah, this is component the current position of this bond. So now, but then the important thing here that I wanted to show you is not only this, but also how this force term that it's explained in here, it's being computed, yeah? And this is something that you might find useful. Why? Because you will see here that it computes the value t that I was mentioning before, this small t here, but in order to, which is being then multiplied by the unit vector of the deformation, which is computed as y divided by the absolute of y, which is written here. Y, the first component, divided by the magnitude, y for the second component, and for the third component, it will give you the vector of the force Fx, correct? So now you have the vector, obtain the vector t. In this moment, we will not be looking into the damage parameter here. But then the important thing here is how is this notation interpreted? Like in here, it is computing the force in a particle X, and whereas here it's computing the force in a particle Q. Aren't these values the same? And the answer is, yeah, it is the same. So we were mentioning that the force that is acting upon the particle X must be actually the same as the force that is acting upon the particle Q. So, and this is actually, they need to be the same. And this is important to mention because otherwise, because this way we will ensure to be establishing continuity between this, and this will be obeying a linear momentum continuity equation, which means that otherwise, if they were not the same, we wouldn't have a continuity and we would be violating a physical law. And for this peridynamic formulation to work, these force terms, they must be actually the same. That's why. But here on the state-based peridynamic equation of motion, this, as you recall, this term here is being multiplied by the volume of the particle Q, which is, we are looking at this picture here, it would be multiplying every force that it's being computed for every bond here would have to be multiplied by the volume of this particle Q. Yeah. And some very frequent question that is being asked in the peridynamics community, especially when you are starting to look into this code and dig in, it's why, for instance, the force here that we have computed here, the vectorial force here, is being computed here for the self volume, and here it is being multiplied for the self volume. And if you go into deeper here, you can see that the self volume here belongs to the volume of this particle n. Yeah. Whereas here this self volume belongs to the volume of the particle here, to the volume of the particle P. Yeah. So in other words, the cell volume belongs to the volume of Q, which is what you want, since this would all be multiplied by the volume of Q. But the cell volume belongs to the volume of this particle X. And this is not showing in this equation, right? So this sometimes confuses the other, people who is starting to look into the code. Why is this multiplied by the volume of Q? And the reason is quite simple. It's just a matter of how the code is programmed here, because as you can see here, in the first part, doesn't it completely makes sense? You compute the force vector, then you multiply it by the self volume, and then you accumulate the value to this cell that, as you see here, a pointer that's been accumulating all the value here into the force that is being experienced by the particle X, which means this one. That expression, it's computing and accumulating the force that is being accumulated into this particle X by all the particles. But this other term here, it's accumulating it in the particle Q, which is here, with a minus sign, and it is multiplied by the self volume. And this is the question. Why is this happening? So, and the reason is quite simple, because let's say you have finished to compute all the force interactions with all the particles that belong to the horizon of X. Then you go to the next particle, which is Q here, and then you start computing all the bond interactions with respect to this Q. Eventually you will reach again the X here, right? And you will compute the first term, as we were mentioning before, as this time would be X minus Q, and this would compute the first part of this expression. But for the second, and this would be multiplying by the volume of X, right? Because it's the cell volume, which if we are looking now into this picture. But then if we wanted then there is also the second expression in which Peridigm computes the same force, which has to be the same, of course, and then it's multiplying by the volume of Q, right? Because it will be the cell volume in this case, right? And this is accumulating it on X, right? As we were mentioning here, it is accumulating it on the local ID on X, which is on this particle here. So since this is accumulating it on X, and it is multiplying it on using the self volume, the volume of Q, now this initial particle that will get this value that has been provided by this when using the second expression. So here it would be computed the second term expression in here, where it is being actually multiplied by the volume of Q, which in this case is computed, but this part, this second expression, it's only being obtained once you have you started to compute all the bond interactions that on the neighborhood on the neighborhood of this particle Q. So that's why it's being done in 2 steps. But the result is exactly as expected. This whole expression is being multiplied by the volume of Q then for each of those. So this is the reason why. I hope this makes clear this part. If this is not very clear, please let me know and I will share my comments with you. So, and I think we have covered a lot this for today video. Let's leave it like this. During my next video, I will explain to you why is the difference between the formulation when using small f and when using capital T, and where these materials actually come from. And again, we will also look into the code and yeah. So I hope you really enjoyed this video. Give it a like if you enjoyed it. Please subscribe to my channel and be aware that I will be uploading videos every week. So I will keep you updated with all the recent news of the development that is going on. Thank you very much and see you next time. Bye bye.